Everything you have ever known, every person who ever lived, every star you have ever seen in the night sky, every planet, every galaxy, every atom of matter in the entire observable universe. It will all end, not in a dramatic explosion, not in a single moment of destruction, but slowly, quietly, over a period of time so incomprehensibly vast that the entire current age of the universe would appear as less than a single heartbeat by comparison. The universe is dying. It has been dying since the moment it was born. And tonight, I'm going to take you to the end. We are going to travel through time, far beyond the last star, far beyond the last black hole, all the way to the final moment. The moment when the universe reaches its last possible state, and there will be nothing left. But before we get there, let me show you what we have right now. Right now, the universe is alive. Stars are being born in nebulae across hundreds of billions of galaxies. Planets are forming around young suns. Life, perhaps, is emerging on worlds we will never know. It is beautiful, and it is temporary. We begin our journey 1 trillion years from now. 1 trillion years. The universe today is approximately 13.8 billion years old. 1 trillion years is roughly 70 times longer than the current age of the universe. And at this point in time, the last stars are beginning to die. Our sun will have been gone for nearly 1 trillion years by now. It burned for approximately 10 billion years. Then it expanded into a red giant, swallowed Mercury and Venus, possibly Earth, and then collapsed into a white dwarf. A white dwarf is what remains after a star like our sun burns out. It is approximately the size of Earth. It contains the mass of a star, and it simply sits there, slowly cooling, for billions and billions of years. But 1 trillion years from now, even the smallest, most efficient stars will be burning out. These are called red dwarf stars. They burn so slowly, so carefully, that they can survive for trillions of years on a single supply of fuel. But eventually, even they run out. Imagine standing on a world orbiting one of these last stars. You look up at your sun. It is dim, red, ancient. You look out into the night sky around it, and you see nothing. No other stars. No galaxies glowing in the distance, just darkness in every direction. Because by this point, the galaxies around you have either merged into one enormous structure or drifted so far apart due to the expansion of the universe that their light can no longer reach you. You are alone in the darkness, orbiting a dying ember, with no knowledge that anything else exists. And then your star dims and goes out. The era of stars is over. For the first time since shortly after the Big Bang, the universe contains no burning stars. It is dark, but it is not empty. Something else is still out there. Something that will outlast the stars by almost incomprehensible amounts of time. Welcome to the black hole era. The time period that we are now entering spans from roughly 1 trillion years to 1 Google years. A Google. That is the number 1. Followed by 100 zeros. That number is so large, it has no physical meaning. There are only approximately 10 to the power of 80 atoms in the entire observable universe. A Google is 10 times larger than that. And the black hole era lasts for Google years. During this era, the universe is not completely empty. It is filled with the remnants of dead stars, white dwarfs that have cooled completely into black dwarf stars, neutron stars, the occasional rogue planet drifting through the darkness with no sun to orbit. And black holes. Black holes are the universe's most patient objects. They formed when the most massive stars collapsed at the end of their lives. And since then, they have simply waited, growing slowly by consuming anything that strays too close. In the early universe, black holes were terrifying, violent, active, Supermassive black holes at the centers of galaxies consumed matter at catastrophic rates, shooting jets of energy across millions of light years. But now, in this dark and quiet era, they are still, patient, waiting. But here is something remarkable. Black holes are not permanent. In 1974, a physicist named Stephen Hawking made a discovery that changed everything we thought we knew about black holes. He discovered that black holes slowly leak through a quantum process that occurs at the very edge of a black hole's event horizon. Tiny amounts of radiation escape. This is called Hawking radiation. It is almost impossibly slow. A black hole the mass of our sun would take approximately 2 times 10 to the power of 67 years to fully evaporate. The supermassive black holes at the centers of galaxies, the largest objects in the universe, would take approximately 10 to the power of 100 years. But they do evaporate. Every black hole that has ever existed, every black hole that will ever exist, will one day reach its final moment. At that final moment, the black hole releases all of its remaining energy in one last burst of Hawking radiation, a brief flash of light, in an otherwise completely dark universe, and then it is gone, one by one, over incomprehensible spans of time. Every black hole in the universe evaporates. The last black hole to evaporate releases its final flash of light, and the universe goes completely dark for the first time. The black hole era is over. What comes next has no name in any human language that does it justice. The dark era. There is no light in the universe. There are no stars. There are no black holes. There are no galaxies. The universe at this point consists almost entirely of nothing. And yet, not quite nothing. Spread throughout the incomprehensible darkness are subatomic particles, electrons, positrons, photons of almost zero energy, neutrinos, spread so impossibly thin across so impossibly vast a space that the average distance between any two particles is larger than the current observable universe. The universe is effectively empty. But is it truly empty? Some physicists believe that even in the dark era, something remarkable can still happen. Through a process called quantum tunneling, particles can do things that classical physics says are completely impossible. They can pass through barriers. They can spontaneously rearrange. They can form structures that should not be able to exist, given enough time. And we have an almost infinite amount of it now. Some physicists believe that random quantum fluctuations could cause particles to spontaneously arrange themselves into complex structures, even living structures. This is called a Boltzmann brain. The idea is this: given a truly infinite amount of time, anything that is physically possible will eventually happen, including the random spontaneous formation of a fully conscious brain, complete with false memories of a life never lived, existing for a brief moment in the darkness, before dissolving back into nothing. Imagine that. A mind, alone, in the infinite dark, with memories of a childhood, of people it loves, of a sky full of stars it has never actually seen, existing for a fraction of a second, then gone. Whether Boltzmann brains actually form is still debated among physicists, but the fact that we must consider it tells you something about the nature of a truly infinite darkness. The dark era continues, for longer than any number with a name can describe. And eventually, even the subatomic particles may decay. Protons, the particles at the heart of every atom that has ever existed, may not be stable forever. Some theories predict that protons decay with a half-life of approximately 10 to the power of 40 years. If this is true, then by the time we reach 10 to the power of 100 years from now, all matter, every atom, every particle of material substance that has ever existed in the universe will have decayed into radiation, and then the radiation itself spreads out, dilutes, cools toward absolute zero, and the universe enters its final state. Heat death. The name is misleading. Heat death does not mean the universe becomes hot. It means the opposite. Heat death is the state of maximum entropy. Entropy is the measure of disorder in a system, and the universe has been moving toward maximum entropy since the very first moment of the Big Bang. Think of it this way. When you drop a glass on a floor, it shatters into 1,000 pieces. You never see 1,000 pieces spontaneously leap off the floor and assemble themselves into a glass. That is entropy. Things move naturally, from order to disorder, from complexity to simplicity, from structure to chaos. The universe began in an extraordinary state of low entropy, tightly packed, ordered, full of potential energy. And since then, it has been unwinding, stars burning their fuel and releasing it as light and heat, spreading energy across space, increasing the disorder of the universe with every passing moment. Heat death is the moment when this process completes. At heat death, the temperature of the universe approaches absolute zero. Absolute zero is the temperature at which all thermal motion stops, the point at which there is no energy left to do work, no hot regions, no cold regions, just perfect, uniform temperature throughout. And in that state, nothing can happen, not because it is forbidden, but because there is no energy gradient to drive any process, no difference between here and there, no reason for anything to move, no way for any structure to form, no possibility of any event. The universe has not exploded. It has not collapsed. It has simply equilibrated, like a cup of hot tea left in a cold room. Eventually, the tea and the room reach the same temperature, and nothing changes after that, forever. This is the fate of the universe, not with a bang, not with a whimper, but with a silence so complete that the concept of silence itself no longer has meaning, because silence requires something to be silent, and there is nothing left. But wait, I want to tell you something that most people never consider when they think about the end of the universe. The end we have described is not necessarily the end. Some physicists believe that even after heat death, even after the universe has reached maximum entropy and sits in perfect eternal stillness, something can still happen. In quantum mechanics, there is a concept called vacuum decay. The idea is this. Our universe exists in what physicists call a false vacuum, a state that appears stable, but is not actually at its lowest possible energy level. Like a ball sitting in a small dip on the side of a hill, it appears to be resting, stable, but below it, far below, there is a lower valley, a true minimum. At any moment, anywhere in the universe, a quantum fluctuation could push the ball over the edge, and if that happened, a bubble of true vacuum would form, expanding outward at the speed of light, changing the fundamental laws of physics as it grows, rewriting reality itself in its wake. Everything inside the expanding bubble would be reconfigured, not destroyed in any conventional sense, but transformed into something operating under entirely different rules. A new universe, with new physics, new possibilities. We would never see it coming. It would travel at the speed of light, and nothing travels faster than light, so we would have no warning. One moment existence, the next moment something else entirely. Some physicists also believe in the concept of eternal inflation, the idea that our universe is not alone, that it exists within a vast multiverse, where new universes are constantly being born from quantum fluctuations in an eternal sea of space. If this is true, then the death of our universe is not the death of existence. It is merely the death of this particular chapter of existence, somewhere in the multiverse. Right now, a new Big Bang is occurring. A new universe is being born, with its own laws of physics, its own stars, its own galaxies, its own planets, perhaps its own life. We will never know. We cannot know. Our universe will end before any signal from beyond could ever reach us. But the possibility, the mere possibility, that existence itself does not end with our universe, is perhaps the most beautiful thought that physics has ever given us. We began tonight in a universe full of light, full of stars being born, planets forming, life emerging in the darkness. And we have traveled to the end of all of that, to the last star, to the last black hole, to the last particle, to the last possible moment. And here is what I want you to carry with you when you close your eyes tonight. You exist in the most remarkable era of the universe's entire history. The stelliferous era, the era of stars, the only era in which the universe burns with light, the only era in which warmth exists, the only era in which complexity can form, the only era in which life is possible. Out of a timeline that stretches to 10 to the power of 100 years and beyond, you exist in the first 100 billion years. In the dawn, the universe spent 13.8 billion years creating the conditions for you to be here, forging the carbon in your body inside dying stars, scattering it across space in supernovae, gathering it on a small blue world, waiting for it to learn to think, waiting for it to look up and ask, what are we, and how long do we have? You are the universe, looking at itself, while it still can. Sleep well. The universe isn't ending tonight. Tonight, it's still here. And so are you. If this journey moved you, subscribe to Decode Deep Space. Every week, we travel somewhere the universe has never taken you before. And there is so much further we can go.